Hello, everybody. Welcome to section 2.3. This section is on using graphs of functions to get information about the functions. There's actually quite a bit of information we can get from functions by looking at their graphs. So there's quite a bit of little topics to cover in this section. So let's go ahead and get started. The first kind of skill that we're going to look at is going to be finding domain and range. From the graphs of a function. So we can find a domain and range kind of like this. So if we draw a graph, x-axis, y-axis, and then let's do something like this. So let's say we have this kind of graph, this kind of curve here. And we want to know what its domain and range is. So to find its range, what we're going to do is we're going to look at what values on the y-axis match up with the graph, like this, right? So if you draw little like lines going to the y-axis, wherever those lines hit in between, that's the range, right? You can imagine if you take the graph and you squish it against the y-axis, wherever the graph is going to get squished to, that's the range. So the range is these points and everything in between. Finding the domain is pretty similar. You draw little lines down to the x-axis this time. And so you can imagine if you took your graph and you squished it against the x-axis, wherever the graph is getting squished to, that's the domain. So in this case, the domain is these 2 points and everything in between them, like that. So let's look at like maybe a more concrete example, something that maybe might be on your homework for example. So if we find the domain and the range from the following graphs. So let's do maybe something like then let's draw this graph. Let's do let's start it here. And I want it to go up to 2, 3, oops, here. Open circle, I'm going to draw a curve there. And then I also want a point here. Okay, so let's say we have this graph right here. Let's find its domain and range. So first off, for the range, take little dots out to here. And then we also did this one out here and bring it into there. So if we squish both sides together into the y-axis, we get this point here for sure. We get everything up to here. And then because this point here isn't like a part of the graph, it's a little hole, the range is going to have a hole here too. So our range is going to be from this point, which is 1 inclusive, to 1, 2, 3 parentheses. Cool. And then let's look at our domain. So if we do the same thing, we squish it down to the x-axis. We get a solid point right here, a solid point right here, everything up to this, and then just like the range, we have a hole here again because of that hole there. And so the domain is going to be, so this interval is, 1 inclusive all the way to 1, 3, unioned with this point right here, can't forget it, -2. Excellent. Oh my goodness, I just realized that should be a 4. Some of you all are probably yelling at me through the internet patch right now because I can't count, but that should be a 4. So it's 1, 2, 3, 4 right there. Okay, let's look at another graph. Let's look at another example. Let's do maybe something that we'll see a little more often. Let's look at a parabola. So let's make a parabola in this shape. Let's start it here, and then let's go up and out. So this is where f of x is x squared minus 2. So when we look at the domain and range of this one, so if we look at the range first, if we smush it down to the y-axis, we start at this point here. All right, that's the y-intercept, and then it's everything above that, right? Because the parabola keeps going on to infinity, so it's everything above that like this. And then the domain for this function is, we saw in previous sections that the domain for parabolas and other quadratics like this, the domain is the whole real line. So we already know that the domain is going to be everything, but we can kind of see this because if we took any point on the x-axis, we can draw a little line out to the graph from it, right? So range will be starting on -2 all the way to infinity, and then our domain will be everything. All right, cool. Let's switch gears a little and let's look at finding increasing and decreasing sections. On a graph. So if we look at like a sample graph again, and then maybe I draw something like this. It goes up and then goes down. Maybe it's flat a little bit, and maybe it kind of keeps going up like that. So we want to know where is this function increasing and where is it decreasing. So if we go from left to right, that's the same thing as asking, okay, where is this function going up and where is it going down? So for increasing, we see that this first section here, this is increasing because it's going up. And then this section right here, right, it's going down. So this is decreasing. Oops. And this next section is flat. So this one right here is neither. It's not increasing or decreasing. And then this last section here going on is increasing. So if we were to look at this, so this is a cool picture and it kind of illustrates the idea. But if we look at this in words, so increasing is, so increasing on an interval. So some interval I. So function is increasing on interval I if that function f of x1 is less than f of x2 whenever x1 is less than x2. So to see this on the picture, if we go up here and look, if we pick like this our x1 and this is our x2, and we go up, this is f of x1 right here, and go up. This is our f of x2, and we see that f of x2 is bigger than f of x1, and x2 is bigger than x1. So this is good. That means that this definition makes sense. So this is indeed an increasing section. And so for decreasing, we have, so a function is decreasing on an interval I if f of x1 is greater than f of x2, whenever x1 is less than x2. So if we go up here and we look at our little decreasing section, we kind of do the same thing. Actually, let's not do yellow. It can get confusing. Let's do green again. So if we do this x1 here, this x2 here, not a lot of room. There's one of them, and there's the other. And you'll see they kind of flip places, and that's because it's a decreasing section. So let's look at maybe like a concrete, like homework kind of example. So let's identify where the function is increasing and decreasing. So let's draw our graph. And let's make it maybe something like this. I want to point here and to here, and then 2, 3, 4 here. And I'm going to connect them like this. I'm going to do like a parabolic looking thing here, and then I'm going to do a line up to this one. Oh, this point is in the wrong spot. That's why it looks bad. There we go. That's better. Okay, so we want to know, where is this thing increasing and where is it decreasing? Well, if we look at just from left to right, where it's going up and where it's going down, it looks like it is increasing here. And then it's also going up in this section right here. So this is also increasing. And then it's decreasing right here, right, because it's going down. So this function is increasing on, so all the way from negative infinity to 1, 2, 3, this point right here, which is -3. And it's not increasing at the very top. The very top is a stable point. It's a local maximum, which we will talk about in a second. So we use parentheses here. And then it's also increasing on -1, 2, 2, 2, right here. So we'll union them together. -1, 2, like that. Excellent. Okay, and then it's decreasing on this little section right here, and that's -3 to -1, like that. Excellent. Okay, we have one more kind of idea that we want to cover. There's one more piece of information in this part that we want to talk about extracting from the graph of a function, and this is talking about local minima and local maxima. So local minima and local maxima, they are like the low and the high points, right? So if we look at maybe just a random curve, maybe something like this. I'm going to make it end and then go off that way. If we look at the points that are like the high points compared to like the section of the graph around it, we see that like this right here is a high point and this right here is a high point, right? And then if we look at the low points, it's like right here, right? You might be thinking, oh, that goes off to infinity. Shouldn't there be a low point over here? And no, because there's no point where it like stops getting low. Like there's no minimum there. So if we label these, this will be a local maxima right here, and then local minima here. Okay. Just like increasing and decreasing, we do have a definition that we can write down for this. So we have a local maxima, so the red points up here, at some x equals a, if f of a is greater than or equal to f of x for all x in some interval around a. So that sounds really complicated, but if we go back up at our graph and we look at it, that means that, so if we look at x equals a right here, and if we have like a little like area around it, this little interval, if we pop that up to the graph, we see that there's nothing higher than the local maxima in that interval, which is good. That's the definition of local maxima. And then over here, even though it's like at the end point, there's still this interval here. We can look at sort of the interval with the closest end point right there. And so then this looks like this, right? And for local minima, at x equals a, if f of a is less than or equal to f of x for all x in some interval around a. So up in our drawing, if we look at our little local minima there, our interval would be just this thing right here. And if we pop that up to the graph, nothing in the interval gets lower than our green point, which is good. That's what we want for local minima. So let's look at, again, an example of maybe a question you might be asked on your homework and such. So identify all the local minima and maxima. Oops. And let's draw a graph. Let's do kind of the same thing that we had a couple minutes ago. So okay, and I want to draw this. So we have this point here and this point here, and then 2 up here. I believe, yes. And then a parabola looking thing, and then our line. So we want to identify all local minima and maxima for this function. So we just want to look at, well, first we look at the maxima. We want to look at where is like, where we have our little top parts, the little peaks, right? You see we've got one here at this top. And you might be tempted to be like, oh, what about this one right here? Well, the problem with this one is that, especially if we look at the definitions we have up here for local maxima and local minima, we require that the function be defined at the point, right? So even though this right here is high up there and it is kind of a peak, because the function is not defined there, there's no actual graph, that is not a local maxima. So we're not considering it one. Oops. And then if we look at our local minima, our little low points, we see that we do have one right here. So local maxima is going to be this red point, which is 1, 2, -3, and then 1, 2, 3, 4 up. And then our local minima is going to be -1 and then 1 up. All right, excellent. So those are the three ideas, the three pieces of information we're pulling from graphs in this part of this section. So we talked about local minima, local maxima, increasing and decreasing functions, and then we also talked about finding domain arrangement graphs. So keep working on your homework, and I hope to see you in office hours.